different object like Q1, Q2, Q3, L1, L2. And because we don't have right sector, so the right components of the charged lepton, we don't have neutrino rights in the standard model. We have only charged lepton right and the quark right. And in fact, this was the best or the most interesting mistake happened while you are building the standard model. Because at that time, people, not only Salam and Weinberg and Glashow, people even before Landau and Marshak and other people were contributing in building the standard model, they thought that the neutrino is massless, because at that time, the neutrino is massless. We just discovered recently that it has a very tiny mass. So to construct model with massless neutrino, they assume that the neutrino has no right-handed neutrino and it is only left-handed and they contribute to the interaction of the weak interaction via the left-handed component. And as I said, was not correct. It was a mistake, but very interesting and very important. And it was very useful mistake, in fact, because if they assume the right-handed neutrino, and even they try to find some way to include the right-handed neutrino for the symmetry between the right-handed charged lepton, right-handed quarks, and then they try to impose some, I don't know, symmetry or something to make the neutrino, light neutrino massless. This would not allow them to construct the standard model, but will allow them to construct a much bigger model, and it will be left-right model that I will discuss it today. So fortunately, they did this mistake. They neglected right-handed neutrinos, and they constructed a standard model with only left-handed. And due to this kind of left-handed neutrino, we have only left-handed doublets because we have only SU2 left. No right-handed doublets, and therefore, if we have particles with right-handed, this would be singlets. Singlets under SU2 left means they are separate in separate component like this. They don't live in doublets, and they do not feel the interaction of SU2 left. They may feel the interaction of the hypercharge because they are charged under SU2 under U1 hypercharge. They are charged under SU3 like quark, the quark up or down quark right-handed, but they are not, they are neutral under SU2 left. So this is the way of constructing the standard model based on this assumption and based on this mistake. It's very important to tell you that, due to this assumption that neutrino was massless, we constructed the standard model in this way. And now, because neutrino, it turns out to be massive, and we introduced and we induced the right-handed neutrino back, so we have to think again, maybe we should construct it in a different way. Maybe now we reveal to the left-right model again. Anyway, let us continue with the setup of the standard model. As I told you, for example, the quark is quark left-handed, the Q, the doublets is charged under SU3, charged under SU2, charged under U1 hypercharge. Therefore, when we do the covariant derivative, I hope people knows what we mean by in the gauge theories when we go from normal derivative to covariant derivative. You have the normal derivative plus you add your gauge field, which we added or we introduce it to make the theory gauge invariance. And then the covariant derivative becomes on this definition. They are charged under SU3, so you have a coupling GS, strong interaction coupling, time the generator of SU3, time the gluons, the fields of SU3, and then W for SU2, and this what we call B mu for the U1 hypercharge. So this type of particles, which is quark, left-handed quark, is charged under everything, and therefore it has a very large covariant derivative. But lepton, for example, left-handed, it is not charged under strong interaction, under SU3. So the covariant derivative will be just normal derivative times the SU2 contributions in the covariant derivative, which is W mu A times the generator TA or tau A. And of course, is it charged under U1 hypercharge. So we have this kind interactions or the covariant derivative of the left-handed leptons. Imagine that we have right-handed leptons or quark. No, quark will have, even if it is right-handed, will be charged under the SU3. But this interaction, I should not write it for FR, but LR. ER or mu R, because it is charged only under the U1 hypercharge. Anyway, and we realized that the hypercharge combined with the isospin, the third component of SU2, gives the electric charge. And this is interesting because now the electric charge, you know, people was trying to understand what is the electric charge, how it comes from, and so on. It comes now from these relations, and this is now is giving you some deep understanding for the electric charge as a combination coming from, because this is the U1 which is remnant from the SU2 left times U1 hypercharge symmetry breaking, as we will discuss. Because in nature we know that the up quark is different from down quark, neutrino is different from the electron, then this type of symmetries, in fact, has to be broken. And also because the gauge symmetry makes all these gauge boson, G mu, W, and B massless. And in fact, we know that W, especially W, gluons is massless is okay, because this is we know that it is, and the photon massless because this is long range force, but W is or W mu A in general, which will be W and Z after while, this should be massive because this is really short range force, and for short range force like the weak interaction, the gauge boson should be kind of massive to not be transferring. How to break this symmetry and how to generate mass associated gauge boson, and then also for fermion masses and for motors. This was an issue in the standard model, and it was solved because you cannot break the symmetry explicitly. You cannot add mass term by hand and all this stuff. You know, really, it requires a course in the standard model and the quantum field to show you all the details, but I'm sure people already know, some of you already know, some of you will know soon. So we are giving kind of overview, and maybe you remember these stories when you started to study in details systematically. So how to do this? Was Higgs mechanism, and in fact it was very interesting, and people was not believing that this type of simple mathematical exercise would be physical and realistic. And it works by assuming some potential for the scalar field. You add now, and this was an issue which was not very interesting in the standard model, that you build your model based on gauge symmetries and your fermions, which is doublets or triplets or whatever under this gauge symmetry. No scalar fields needed for this model, but now you need to impose it by hand. You add it to the theory to break this symmetry spontaneously. And you added, it has to be charged under the symmetry that you will break it, because the vacuum of this particle should non-vanish, and this particle should be charged under some symmetry to break it. So they have to be doublet, because you want to break SU2 left cross U1 hypercharge, those symmetries which is not exist in nature now, and we should replace them with a U1 electromagnetism. So you should break it in very smart and clever way. So your field, which we call it Higgs field, should not be charged under SU3, but must be charged under SU2 left and the hypercharge U1. So for that reason, we choose it in this way, phi plus phi 0 as a component of this with a hypercharge 1. And then as any scalar field theory, you will have this this Lagrangian of the scalar field, kinetic term, covariant derivative depends on the interactions of phi field or the charge of the, so it will be like the covariant derivative will be like the lepton doublets, because it is exactly interacting like lepton doublets. So it will be with W mu and the B mu. So we will have similar expression like this one for the covariant derivative here. And then we should have some scalar potential, V of phi. And the scalar potential people know very well that its simple form for the scalar potential is m square phi square plus lambda phi to power 4. Well, we use this, but if you use the m square or mu square phi square and lambda phi to power 4, you should be careful somehow. First of all, lambda has to be positive. Otherwise, this term phi square, phi to power 4, for very large phi and with negative lambda, you will take your potential down to minus infinity. So it will be, it's called unbounded from below. So to guarantee that your potential is bounded and physical, then lambda must be positive. This is easy and this is normal assumption accepted. But now if you take mu square positive and you try to plot your potential, you will not find this shape, but you will find that the potential is just having a minima around the phi equals 0. And in fact, phi equals 0 will not break anything, so because the symmetry will remain exact. So you need to get the minima around the point different from 0. Here it is. And you make the 0 somehow unstable maximum. So this is what forces the people to consider the mass term, mu square term with negative sign. And this is something, again, unnatural. Why you take scalar field phi with negative mass square? This is the tachyonic field, or what is? In fact, it was, people who was criticizing this, they also have the right to do this because this was not convincing them. However, because this is just bare mass in the Lagrangian, is not the physical mass of the field, we still will break and will change things and will mix. So people try to convince that this minus mu square is just bare parameter. You don't take it like physical mass and try to proceed. And if you proceeded with this, but it was an issue, and the new physics we considered, especially in supersymmetry, one of the advantage is to explain how you get this mu square negative and how you can construct a physical model with such scalar potential. Anyway, you take this scalar potential, you make the minimization. Now you can find a non-zero VEV. VEV means vacuum expectation value, the minimum of the potential. We call it V, and this is the one we call it non-zero. And now this V, if you select this minima, because it is not just one minima, it is a kind of circle. You see it is different minima around this value. There is a phase. But anyway, if you take this minima and you fix the minima at this value, then you break the symmetry and you start to generate mass term for the gauge boson, which was massless. The W mu of the SU2 left and the B mu of the U1 hypercharging, the gauge symmetry prevent any mass term for the gauge boson. So you have to break it to generate the mass. And indeed, once you break it with the vacuum expectation value V, then you start to generate the mass of the gauge boson. Mz and Mw started to be non-zero, and is proportional to V square times the gauge coupling, V square times the gauge coupling of the H symmetry. And this is the reason why we have it. If V equals 0 around the minima, when we have the mass term square is positive, the mass will be identically 0 and the symmetry will remain exact. The gauge symmetry will not be broken. It is broken only when we go to non-vanishing wave. And this is very nice relations for the masses of the gauge boson. But of course, we don't work with the nice relation. If it is nice relation, but it is based on not very nice expressions, scalar potential. For scalar potential, we started with minus mu square. So don't tell me that we represent the mass in terms of the vacuum energy, the minimum vacuum energy of the Higgs field time the gauge interactions, and then we started to discuss the meaning of the mass in this case. That's fine. But first of all, really in physics, we are very pragmatic. We have a predictions now. And the people started to believe in this mechanism when they started to make some predictions and they tested. So the MW was known from even before the standard model, from Fermi theory and from V minus A, when we try to explain the weak interaction with some gauge boson mediate the weak interaction on mediate the simple beta decay, we know that the G Fermi, which we measured or we determined from our previous measurements with 10 to minus 5, it should be equal somehow the gauge coupling G2 square over MW square. And then we realize it that MW should be of order 80 GeV. So MW is not new, but people use MW, the value of MW, 80 GeV, to say, okay, we know MW, we know G2, then we know the VEV. And it turns out the VEV to be 174. Okay, but now you should be able to predict new particles. It's called Z, which is neutral gauge boson, which was not known. And in fact, beta decay doesn't really require Z. In fact, the standard model and SU2 symmetry enlarged the weak interaction beyond just simple beta decay, which was mainly based on the charged current. It showed that we could have also interactions, weak interaction based on neutral currents. And in fact, the discovery of the neutral current was even, the first success for the standard model. And then it comes the prediction of MZ. If we have the V is 174 and we know the gauge coupling, we can predict the MZ. In fact, the prediction of MZ was of order 90 GeV from these values. And this is what the people measured later on. And once they observed or probed the MZ with this right value of the mass, was a great success, and the people started to believe that the standard model is correct. And the Higgs mechanism, maybe it is true, or maybe mathematical trick that gives such values and such lengths and blah, blah, blah. But as I said, the physicists are very pragmatic. Give me some predictions, some new results, and test it. Then I trust your theory, even if I do not understand it completely, or I don't understand the setup or the mathematical consistency of it. Unfortunately, in the physics, we wish to have a consistent and mathematical rigorous theory, but not really. This is maybe necessary, but not sufficient. And sometimes we don't need it to be necessary even. The sufficient and the necessary condition is really to have a prediction and observation and testing your theory. Nice things happened also in this model, that you do not only generate mass for the gauge boson, but even the fermion masses, leptons, quarks, everything which was massless due to the gauge assumption, gauge symmetry. It's now the gauge symmetry is broken, and now it is generated. The masses are generated. And they are generated in terms of the same vacuum expectation value. So you see all the masses becomes related to each other. All of them are given with one source, the vacuum energy, and the energy which was given in the Einstein relations, E equal mc squared now is a source of the mass, some energy, some vacuum energy. The minimum, the lowest energy states in the Higgs field is the source or the responsible source for all masses that we are working in. So why the masses are different? Because they are interacting with the Higgs with different couplings. The W interact with the G2 because the Higgs is SU2 left. So it has an interaction with W boson with G2 from the, you remember the covariant derivative that I wrote. And for Z, it has a G2 and G1. So this is a combination of the U1 comes from the B mu and from, because it's neutral gauge boson, which is coming also from the W3, the third component of SU2. For that reason, it has a combination of the gauge coupling G1 and G2. Now, the fermions interact with the Higgs via what we call it Yukawa interaction. This is the Lagrangian of the Yukawa interaction. We have a doublet, lepton or quark, and we have a Higgs doublets. So doublets you can construct singlets, and then it coupled with E-right singlets. You can count also the charge U1 hypercharge, you can count everything, you find it is invariant. So these terms, all these terms are invariant and are allowed to be in your Lagrangian. We call them Yukawa interaction because two fermion, one scalar. We have a scalar field now phi, and we have two fermions. So okay, you have to take care of all SU3 cross SU2 cross U1 invariants. And if they are there, then this term are allowed. And the coupling is different from the usual SU3 and SU2 gauge coupling. This is what we call Yukawa couplings. And in fact, Yukawa couplings, as you can see, they are a lot. They are giving in terms of the flavors, I and J. So this is matrix 3 by 3, which you have to diagonalize to go to mass eigenstates or physical eigenstates and so on. Anyway, the masses will be, once the Higgs will take vacuum expectation value, it's giving you the mass which is V times the Yukawa. So we understand now the interaction vertices, interaction couplings, either gauge coupling or Yukawa couplings makes a difference between different masses. Unfortunately, the Yukawa is not determined or is not fixed like the gauge coupling. So for that reason, we don't have a predictions for the fermion masses as we did with the gauge coupling. But we are one step forward. We started to understand all the fermions, top quark, electron, neutrinos, blah, 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 all of them coming from one single source, a vacuum expectation value times different Yukawa. And then your challenge now is to understand the Yukawa coupling, why they are so different, why they are, are too many like this, why there is a hierarchy between top quark and the down, top quark and the up quark, or down quark and the bottom quark, why charged lepton tau and the electron, this difference in masses, we call it hierarchy in masses. And all of this is now related to the Yukawa. So this is what we call it flavor problems. And this is one issue beyond the standard model to understand this. If you want to really to know your physical masses in very complete manner, you need to understand this origin of this hierarchies and all this coupling. Of course, I am going slow, and it seems I will not reach even left, right, but this was necessary introduction to the standard model, so that when we extended, okay, so I can now be fast, because I will ask you to trust me that standard model, as I said, it's wonderful, is perfect, is in excellent agreement with most of experimental results so far. However, we have an issue that indicate the standard model cannot be the final theory and is not the complete theory, and we need to go beyond it. First one is neutrino mass. I think I mentioned, and I will not discuss more about this because now a lot of experimental results, and this is experimental evidence, in fact, for neutrino masses. How to solve, how to make the neutrino mass is to add the right-handed neutrino that we neglected or ignored from the beginning and try to construct this. Can we do it just by minimal modification to the standard model, add right-handed neutrino, and solve the problem of neutrino masses and keep the standard model everything as it is? Yes, it is possible. And forget about right-handed neutrino, put it very heavy. But as I said, this is not very natural. You have to explain why this scale of law. It's not even got scales, it's just intermediate scales. Why this capital N appears only to play role only to neutrinos and nothing else. So this is something really not very interesting, I would say. Dark matter is another evidence for going beyond the standard model, because all the particles I mentioned in our constructions for the standard model cannot be stable, cannot be candidate for dark matter. So dark matter has, the particle should be neutral and it should be stable, and no particle like this in the standard model. Left-handed neutrino or light neutrinos, after we realize it that it is massive, even with such small mass, we try to use it as a hot dark matter, and if it was able to explain the dark matter, then the dark matter problem would be solved, even with a tiny mass of the neutrino masses, because it could be able to explain all missing dark matter. However, unfortunately, because this is a relativistic particle, it's very tiny, it's very fast, is moving with a velocity of light, it cannot really be used to explain the dark matter with large scale structure of our universe. So it has to be rather non-relativistic, what we call the dark matter. And no particles in the standard model can explain this dark matter. We have another evidence, theoretical evidence, a hierarchy problem. I will not go through all of them now, because I wanted to give you a hint about the extension of the left-right model. We have also baryon asymmetry, why matter, no antimatter in our universe. Matter is dominated antimatter. This is called matter-antimatter asymmetry or baryon asymmetry. All this cannot be explained in standard model. And even more theoretical arguments about this gauge symmetry, why SU3 cross SU2 cross U1, why this kind of semi-direct product, why we have 3 generations of quarks and leptons, why the electroweak with minus mu square is needed, and how you can explain it, and so on. So what is gravity? We are working only with 3 forces. Can we really include gravity at some points? Gravity may be neglected because it's very small. We are working with very small elementary particles, and gravity would, but gravity at early universe could play really important roles. Cosmological constant also is an issue which cannot be addressed within standard model. So all these questions, as I told you, are open questions, require some careful thinking and going extension of the standard model, going beyond standard. So let me summarize this part and tell you, even if you didn't study standard model before, let me give you the definition of or our definition for the standard model. Standard model is defined as 4-dimensional quantum field theory. First of all, it is based on quantum field theory, gauge field theory in 4 dimensions. So you have a Poincare or Lorentz invariant in this theory. And then you have a local symmetry, which is SU3 cross SU2 cross U1. This is the identity of the standard model. If you wanted to add extra U1 or you change something, you are beyond the standard. Our standard model is 4 dimensional. If you go to 5, it's not standard model, it's something beyond. Quantum field, you have to admit all the quantum field, constraints and consequences. The symmetry in this way. The particle content, the one we mentioned, the fermions with the doublets, with the triplets, and the one scalar field only. Why one? Because the standard model constructed with one Higgs doublet for economical reason. If you add another Higgs doublet, even if you add another Higgs doublet, you are beyond. This is different model. Two Higgs doublet model is different model. If you wanted to add extra fermions, right-handed neutrinos, or something more, you have to know that you now extend your standard model. So no right-handed neutrino in the standard model, symmetry breaking with one Higgs doublet, no candidates for the dark matter, no gravity. This is the checklist of the standard model. Anything beyond those, then you are outside the frame of the standard. So this is exactly give me the point of how to go beyond the standard model. Simply you started to generalize or to break or to violate one of those definitions. So if you want, I will focus today on the local symmetry. I will not consider SU3 cross SU2 cross U1. Why? Why not? Because you said you constructed this based on the assumption that the neutrino is massless, and now neutrino is massive. So let me find out the gauge symmetry which will accommodate the mass of the neutrino. Naturally, I wanted to trust gauge symmetry. I wanted to use the gauge symmetry even with massive neutrino. I don't want to add ad hoc right-handed neutrino to the standard model. Then you need to extend your gauge symmetry. And this is the simplest and not the simplest, it's not very simple, I have to admit, but really the very natural, it's relate also left to right. Why you have to have left-handed fermions, doublets, and you don't have right-handed doublets? Why you have SU2 left and you don't have SU2 right? So this was very natural after we discovered that neutrinos are massive to go to this model now, because where is the U1 hypercharge? Oh, come on, this is like the U1 electromagnetism. When we extended to the symmetry, which we needed SU2 left across U1 hypercharge, the U1 electromagnetism becomes low energy symmetry, which comes as a remnant symmetry of the symmetry breaking. Now we do the same exercise, SU2 right, which naturally we needed now, times extra symmetry U1B minus L. And this is also very natural symmetry because we know that baryon and lepton numbers are, a kind of symmetry which may be exact at high scales and is broken at low scale. Now SU2 right cross U1B minus L will play the role of producing the U1 hybrid charge. So in a standard model, we invented the U1 hybrid charge because we wanted to get the U1 electromagnetism, that electric charge. And then we try to go backward, not forward. So, or bottom up. So we know the electromagnetism, and we need to construct the high scale, the U1 hybrid charge. So we started to say, okay, we have also isospin I3L, and we try to determine the U1. But here, no, we start everything at high scale. We know P minus L symmetry, we know SU2 right, and then the symmetry goes down to the U1 hybrid charge with the exact number that you derive it or you try to find it out, and then this U1 with SU2 left goes down to U1 electromagnetism. You see that it becomes a beautiful structures. It's natural. You start everything at high scale. SU2 left across SU2 right, symmetric. B minus L exists. In fact, we have something called B plus L is broken usually at early universe, and the remnant U1B minus L. And from B minus L across SU2 right, you get the U1 hybrid charge. And from the U1 hybrid charge across SU2 left at lower scale, you get the electromagnetism. And this is what remain exact with us. Okay, we will go through this symmetry breaking and all this stuff, but let me now tell you that we promoting now the particle content to left-handed doublets, Q left as before, and now Q right. U right and D right should not be scattered separately, different particles. Now they come together in one doublet. We call it SU2 right, Q right, because it is charged or fundamental representation of SU2 right. And also the lepton, I call it L. Now I call it psi L, but it is capital L still. Neutrino and the charged lepton left-handed. We have also right leptons, right-handed doublets, lepton doublets, which has a right-handed neutrino. This is the needs for right-handed neutrino and the E right. So we don't have before this one, and the E right remains alone, and therefore to avoid to having only E right alone, we forced U to be also U right alone and D right alone. But now we are combining this. And as a consequence, we have neutrino right. And as I told you, if from the beginning they try to make it symmetric like this, and right-handed neutrino should also be included, we will construct naturally from the beginning left-right model. However, fortunately, they do not do this. They didn't do this because it is more complicated models. It could hide a lot of details that we learn. And sometimes you try with simple stuff to learn more and to discover and to be sure that it's correct and working, and then you generalize it. Now we are in the position to generalize it. We are expert in understanding the construction and the details, symmetry breaking, gauge symmetry, all this stuff in the standard model. Neutrinos are massive. Right-handed neutrino is now acceptable, is not really something that we should avoid it. And now then you try to construct in this way. This is give you what we call the left-right symmetric model. The Lagrangian, as usual, now the kinetic, we have Q left, Q right, psi left, psi right for the leptons. And here, this is what I was discussing with you about the symmetry breaking. The symmetry breaking will be, you start with SU2 right cross U1B minus L. You start with having some scalar field like Higgs field that break only this sector at higher scale, and they keep SU2 left with U exact. Then at this down scales, you will have SU2 left cross U1 hypercharge. And from this one, you break this with the Higgs doublets. Remember, what we need to break the SU2 left cross U1 in the standard model, the usual Higgs doublet, scalar in fundamental representation, Higgs doublet. Why here SU2 right cross U1B minus L? Why I should break it with different Higgs field? Why I should not try, this is SU2 cross U1, similar to the SU2 left cross U1 hypercharge. Why I don't use doublets as well to break this? This is exactly what we did when we constructed what we called TV scale left-right, because I will show you that people, Mohapatra and people invented the left-right in 70s, or maybe even before, I think 70s. They started to break SU2 right cross U1 B minus L with a joint, not with a fundamental representation. So why a joint? Why not a fundamental like the usual standard model symmetry breaking? I will tell you, and I will tell you why I went to the fundamental, much simpler, much normal, to be generalization of the standard model. You need just to add another Higgs doublets, which is invariant under SU2 right. We call it chi right or H phi right or H right, whatever right, it's doublets, break the symmetry. But let us go step by step quickly. I will try to, summarize it quickly and focus only on the main point. So this is a point now, is really, this is a model that we constructed. We believe left-right symmetry is interesting, is natural, and explaining why why there is a, you explain the violation of left-right symmetry, because in nature, we know very well nature, left and right is not symmetric, but as usual, when you start from symmetric theories and you break it spontaneously or whatever mechanism to break it, then you understand really and you quantify the violations, how it works. This is a conventional left-right. And what is important here to mention to you that they used Higgs sector of this form. Adjoint, call it delta L, which is of course, Higgs should not be charged under SU3. So 1 here means singlet under SU3. 0, it's left. So 0 here is under SU2 right. Seems I wrote right, SU2 right before SU2 left cross SU2 right. But anyways, assignment here for this 0 for SU2 right. And the 2 is doublets under SU2 left with, of course, some B minus L charge. The right, no, I'm sorry. Here 1 is a singlet under no, 1 is a doublet under SU2 left, so there is no charge for SU3 included. 1 is a doublet under SU2 left. 0 means singlet under SU2 right, and the +2 is a charge under V minus L. So delta right will be the opposite. So 0 under SU2 left, 1 under SU2 right, and the same hypercharge, same B minus L +2. Why left and right? They said, okay, we need left and right because we need to have it also symmetric. Well, gauge symmetry SU2 cross SU2 right, different from the parity, left inverted to right or right inverted to left. This is extra symmetry. But when you have a symmetry of the gauge symmetry SU2 left cross SU2 right, is not necessarily that the theory should be invariant under any left goes to any right and vice versa. But in fact, they include left and right not for this reason. They include it because they wanted to break this SU2 right cross U1 B minus L, so they need delta right. Delta right is a charge under SU2 right and has a charge of B minus L. So once you have a vacuum expectation value for delta right, then you will break the symmetry. But they also need delta left because they want to construct neutrino masses, as I will show you now. But anyway, what about this phi? This is kind of bi-doublets. So as if you have 2 Higgs doublets, and at high scale of left-right model, these 2 Higgs doublet combine together and they give you bi-doublets. It's called bi-doublet, which when we break the left-right symmetry, this will be separated to 2 Higgs doublets. So in fact, the effective theory of the left-right model is not the standard model by our definition, but it is a standard model with 2 Higgs doublets. Because automatically you cannot build the left-right model without this bi-doublet. Because this bi-doublet, you will use it to write what we call it Yukawa interactions. And from the vacuum of the capital phi or the components in phi, you generate the masses of four fermions. So it is essential. And you cannot do it with one doublets only. You need the bi-doublet to give mass for left and right. So once you break the symmetry, this will give you two Higgs doublets. So the effective theory or low energy theory derived from left-right model is not the standard model, but standard model with 2 Higgs doublets. But okay, let us go step by step. Here is the potential. I don't want to talk too much about the potential. Here is the bi-doublet. As I told you, it is 2 Higgs doublets combined together. So one of them will be phi 1, 0, phi 1 plus, phi 2, 0, phi 2 minus. The ordering here or the position of each component depends on the charge of B minus L minus +2 that we are saying. This is again the potential, how to generate the vacuum expectation value. And as I told you, you generate the vacuum expectation value by the adjoint, not by the doublets. And this is completely different scenario for breaking the symmetry than the mechanism we used in the standard model. So anyway, the delta, this delta is similar to bidoublet. It is 3 by 3, sorry, 2 by 2, looks like 2 by 2 matrix because it is adjoint under SU2 right or SU2 left, so it is a linear combination, so it is proportional to the generators, which Pauli matrices, so it is 2 by 2 matrix. And the neutral components getting the VEV, because you cannot give a VEV for charged components, so you generate a VEV for the neutral component of delta, which is V left and V right. V left for delta left, V right for delta right. And the capital and the vacuum expectation value for the bidoublets, we have 2 Higgs doublets with phi 10, phi 20. So in principle, you could have a vacuum expectation value here V or V prime or kappa prime, whatever. So you see the Higgs sector is really rather huge. You have delta left, which is 2 by 2 component, 2 by 2 matrix. So how many components? And then delta right, bidoublet phi, and all this. How many VEVs? K prime, V left, V right. So it becomes, for that reason, I told you, fortunately, though we did this mistake in the beginning of the 60s when we construct the standard model. Otherwise, we will be entered in this big mess, and maybe we will not be able to construct some useful physics. Here is the particle content.
Yes. Already 5, but maybe you can take try to wind it up in 10 more minutes.
Yeah, this would be great.
Yeah.
Okay, so the conventional left-right, let me summarize it, and this is what I will tell you about conventional, and I go for the other alternative left-right, I would say. It has this doublets, leptons. I think you agree now, neutrino, electron, lepton. This is the usual doublets in the standard model. New doublets is called LR, where we have new R with ER in one doublet. We have Q left, and we have Q right, and we have W left. W is a standard model, W mu. We have to define now W left for SU2 left, and another W right for SU2 right. So we have a three gauge bosons, W plus W minus W3 for the left, W plus W minus W3 for the right. And then the bidoublet phi, as I told you, it's 2 Higgs doublets combined together. And then we have delta left and delta right, that adjoint representation we used to break the symmetry. But you see from the here, you have delta 0, which gives give non-zero vacuum expectation value, and you break the symmetry. But the content is strange. It has a charged particles and even doubly charged particle, delta plus plus or delta minus minus, and it for left and for right. So in fact, after you break the symmetry, all this charged particle, doubly charged and the one singly charged particle would be physical, and we have to find it out. And this is a kind of a prediction that if we find it, then the conventional left-right model will be perfect, and we will accept it if we are happy with it or not, why adjoint, why not fundamental. All this question will be thrown, and we will use the model. But till now, the search is indicating that it's no any hint for W plus and all these particles. So, okay, there is no any hint for anything new, but it's very difficult to imagine that we have doubly charged particles. This is something is not drawbacks, but something, you know, tricky should be taken into account. Okay, I will skip the details of constructing everything and details of this, but let me summarize the conventional left-right model. We construct SU2 left cross SU2 right times U1B minus L, and this can be broken down via the adjoint to SU2 left cross U1, and then after that you break down to the standard model, U1 electromagnetism. So the problems here, it has very interesting and nice features. It assign give neutrino, generate the neutrino masses. It has kind of left-right symmetry, as we said, but it has some drawbacks. For example, the doubly charged particles that I mentioned. Also, in order to solve or to account for the neutrino masses, because the neutrino masses will be proportional to the vacuum neutrino left, V left, the vacuum of delta L. So vacuum of delta L will generate, delta L will generate the V left, and the V left will be involved in the neutrino masses. So to have very small neutrino masses, you need very tiny V left. So you explain tiny neutrino with tiny V. This is really not nice. So better to take the V left is 0. And then why you take it 0 and why you include delta left originally, then remove delta left, and then you will have only delta right. Don't worry about left-right as a discrete symmetry, because we are more interested in the gauge symmetry, but then started to make deformations for the model. The Higgs sector is very large, but not only difficult to work, but it generates a lot of flavor changing neutral current. You have to be careful because the flavor changing neutral current is not observed, and there's severe constraints from the experimental results. So you have to control this with such a huge sector of left-right model. So all these arguments, encouraged us to think about something else. Think about, the only change I will propose it here is not to you is just to avoid using the adjoint representation in the conventional left-right model in breaking the symmetry. Why delta left and delta right? Why I cannot use chi left or chi right? And in fact, even chi left, I don't need it. So minimal, for minimality, as in the standard model, when we have a minimal one Higgs doublet, we can work with one right-handed doublet. I call it chi right. The rest is the same. You have the left-handed quark, right-handed quark doublets. You have left-handed leptons. You have right-handed leptons, the same. And you have the bi-doublet. This is to be able to write the Yukawa interactions and to have all these masses and Fermi masses and Fermi interaction. And one chi right for breaking the symmetry SU2 right cross U1. Then you will ask me, then how to generate the neutrino masses? Delta left was used to generate neutrino masses, and it was not working nicely, and delta right was making, kind of mass for right-handed neutrino and allowing for seesaw mechanism, blah, blah, blah. How you make it this now? Well, fortunately, we learned it after many, many years that what we call it seesaw mechanism is not the only mechanism to generate neutrino masses. You could generate neutrino masses with another mechanism like the one I will consider here. It's called the inverse seesaw mechanism. And for inverse seesaw mechanism, you need to add another fermions, another singlet fermion, what I call it now S1, and due to the B minus L anomaly, we have to have another S2 with opposite charge. So this S1 and S2, you have to add it to construct what we call it inverse seesaw, and you can be able to generate neutrino masses accordingly. Let me show you very briefly how this is a potential for phi and the chi right only, so much simpler than the scalar potential and the Higgs sector of the conventional. About Yukawa, you have everything. This term was before for bi-doublet tilde, and this is quark bar, which will left-right give you Yukawa interaction and generate masses. The new stuff is in this part. When we have left-right, the right-handed neutrino, coupled with another fermion via the chi-right. So this is doublet right, chi-right, doublet right, exactly as we did in the standard model. Doublet, doublet times singlets. And for that reason, we asked it to add this singlet S. With this, you break the symmetry with the chi-right down to SU2 cross U1, and then you break it with the vacuum of the Higgs doublet phi. The two Higgs doublet will be separated, and any vacuum expectation value of this two Higgs doublet will go down to this. Very nice, and it works as before. You generate masses and all this stuff, and things becomes controlled in favor of changing neutral current. Let me just close the discussion here by telling you how the neutrino masses are generated. In fact, the neutrino masses will be generated with this inverse seesaw, where we have this mass matrix now. Before it was 2 by 2 matrix, 0 M Dirac, MD transpose 0, and not before 0 here there was MR. Now you change the setup and you get it in the basis of left-handed neutrino, right-handed neutrino, and singlet fermion to be 3 by 3 matrix. And due to the symmetry, you are not allowing any mass for neutrino right, but you allow mass for the mixing between neutrino right and S2. And this is will generate this mass matrix. This is known mass matrix. People studied separately without left-right model as another different mechanism for generating neutrino masses, and they call it inverse seesaw. And therefore, we try to implement inverse seesaw in the left-right. It's true that we add one singlet fermions, but we really removed delta left, delta right, all flavor changes. A singlet fermions coupled and mixed with the neutrinos, and they give you the masses. And when you diagonalize, you get very light neutrino masses of this order, even much easy to generate it with MR of order TV, because before that was MD square over MR, and you have to have MR of order 10 to 13 GeV. Now MR, which is coming from the vacuum expectation value of chi R, which is a scale of the breaking SU2 right, can be of order TV scale. Why? Because we have a small mass scale here is called the mu S. And this can be generated radiatively. So everything is controlled and work naturally and nicely to give you very light neutrino mass. And now you don't have only 3 right-handed neutrino, but the 3 right-handed neutrino with the 3 singlet S mixed together, and they give you 6 heavy, we call it right-handed neutrino as well. So this is the model and the Higgs sector we studied, in fact, and we showed that one of those second lightest Higgs could be quite light, of order few hundred GeV up to TeV, and we did some analysis to search for this left-right inverse seesaw Higgs at LHC, but enough, because I take already 15 minutes more than my time, and I wanted to give at least a few minutes for the discussion and the questions. Thank you very much.
Okay, very good. Thanks, Shaban. Yeah, we are maybe 10 minutes beyond, but if there are any questions, we can take them. Maybe a couple of questions.
Even comments from students, they like the idea of left-right, they prefer standard model, they believe that we need beyond the standard model. Please feel free to make your comments if you don't have questions.
Yes, excuse me, Professor.
Go ahead.
Yeah, so what I understood from you is that this is the new approach if we want to study beyond the standard model.
Mm-hmm.
Like, is this then like, do we have a certain approach? Like this is one of the approaches, or we have other approaches also?
If you see the slide where I said the approaches or the directions or whatever for beyond the standard model, one of them is to extend the gauge symmetry. I'm in favor of the gauge symmetry. I believe in the gauge symmetries because really it's giving you, kind of mathematical rigorous background that you rely on to construct the model, not in any ad hoc way. So if I wanted to extend the standard model, I prefer to extend it via extending the gauge symmetry. So the simplest extensions could be either to extend the standard model SU3 cross SU2 cross U1 times another U1 is called U1B minus L to generate neutrino masses via the U1 by B minus L and via the scale of B minus L, because the right-handed neutrino masses and the neutrino masses are violating lepton numbers. So you can say, I want also to make it like a gauge symmetry, the lepton number, but we don't have symmetries called U1L. You have U1B minus L, which can be used as a gauge symmetry, and then you generate. So this is one model, and we worked also this scenario. But if you want really to also consider more elegant extension and to explain the parity violation and left, right, and you make this extension, you go from SU2 left to SU2 left to SU2 cross SU2, this is will give you that model we are talking about. So this is one example of the extensions. One example of possible extensions. So via the gauge symmetry, you can think about all the gauge groups SU3 cross SU2 cross U1 are implemented in one simple group like SU5 or one simple big group like SO10. So we have several ways to go beyond the standard model via the gauge symmetries. I'm giving you example of very simple, and it is not new. As I told you, the left-right started in the 70s, but it started with the conventional models, and now we have learned a lot about neutrinos and about the mechanisms, and we can really think of making left-right at low scale as well.
Thank you, Professor.
Okay, good. Any more questions?
Yes. Professor, which is the role of supersymmetry in this approach?
No, this is non-supersymmetric. If supersymmetry is it is a symmetry which, like in the standard model, we added to improve our model and our result, and then we construct supersymmetric standard model, what we call it minimal supersymmetric standard model. And this solve, as I told you, this minus mu square problem, solve the hierarchy problem. It works. Supersymmetry is very useful symmetry that you can add. So you can decide to add it also to the left-right model because we need it, in fact, and then you will have a different version. It's called supersymmetric left-right model. But be careful because we already extend the standard model to left-right, and now we have doublets and a lot of doublets, and all this in SUSY, it will promote it to what is called superfield, and the model will become rather big. However, it is exists in the literatures and the people studied, and at some point, yes, if we succeed to have any predictions realistic to the left-right model, we may need to include SUSY as well.
Yes, thank you. And about the predictions of this model, at which energy scale do we need to run the experiments to see, for example, the other Higgs?
No, it depends. You see here, for example, because you could have rather heavy particles, and it's still possible to get some light particle that you can try to probe it. So SU2 right, to break it, you need to break it at few TeV. Something like 6-7 TeV, because there is a constraint from the search. But once you break it with this value, the gauge boson, you remember I told you that we have W right, charged W right, and Z prime, the neutral heavy particle, Z prime. We call it prime because the standard model has W and Z, and the new particles, we call it W. those W prime and Z prime becomes, they are proportional to V right. Let me call it V right. So 60V and times the gauge coupling, which could be of order 0.1 or 0.5 or whatever. So it would be of order a few TV. The LHC is searching for the gauge boson W right and Z prime, but they are heavy and still the energy at LHC didn't really produce anything. So this is one. Another things, the Higgs sectors, the right-handed neutrinos, and all this stuff could be much lighter. And then, you know, I told you in the Higgs, we have several particles. This is a charged Higgs, for example. There is a pseudoscalar Higgs. There is a neutral Higgs. And I am giving you now example for the neutral Higgs. So the lightest Higgs should be the standard model light, 125, because you have to keep your standard model Higgs that we measured in the model. And then the second lightest will be of order 500 GeV, 600 GeV. This can be probed. And our analysis here is to show that if you have this H prime, then you can produce it via gluon fusion, and then H prime decay to even to standard model Higgs, and then it goes to 2p to gamma. And this is very interesting signals, which could be somehow control the backgrounds. You know, the backgrounds is still a lot, but you can really use what's called the cuts to, this is a relevant background. So you see how many process could generate the background, a lot. However, we managed to use different cuts so that the background, this is a black curve. It was, you know, hides the signals for the H prime at 400 or 250 and 400. But once you use cuts, people work in experimental or data analysis, they know that they use some constraint to kill the background and to keep the signal survive. So you break this, you see that the signal now can be seen and the background could be really suppressed. So this is indication for that it is possible. There is a hope to probe this extra Higgs, we call it H prime. So this is one example. There's several particles in the model that could be light and could be probed at LHC.
Okay, I think we are way past close time.
Okay.
So I think we can stop here. Thanks very much again, Shaban, for such a thorough review. I'm pretty sure a lot of people and students have learned quite a lot from it. But if you can share the slides with me, if our students look for them, ask for them, that'll be great.
I will send it to you immediately. And anyone from the audience or missed the seminar is welcome to contact me to discuss with him anything he wanted to discuss. Related, of course, to left-right model or particle physics in general. I will be happy to discuss with you.
Okay, great. Thank you very much. So I'll be sharing Shaban's slides with everybody who attended the seminar.
Okay.
Okay, Shaban, see you soon.
Bye-bye.
Thanks again. Bye.